Thank you for a very generous introduction. Some of it is actually true. All right, so here's what I'd like to present to you today. I want to begin by discussing, and now I understand this is a low-tech environment, so I have to do this point. I want to describe the phenomenon of network densification, and so I'll begin by just presenting you some data about networks that densify, and it turns out to be more universal than we think. And then I'll introduce a very simple, like absolutely trivial model we call the copy model that accounts for many of the features of densification. And then I'll present some interesting features about what happens in densifying networks. And so there's all kinds of oddities that are kind of orthogonal things you might have known in sort of what in the so-called field of complex networks. And then if there's time, and by the way, this work is in collaboration with Renee Laviat, who I guess now moved to Oxford, Pasha Polkowski, my longtime collaborator with whom I've now written 77 papers in one book, and a PhD student who just graduated with Tambat. And then if there's time, I'll describe some interesting mysteries about the phenomenon of redirection, which turns out to be an incredibly efficient way to generate complex networks. But still, there are many things about this that are unknown and very weird and very open. Okay, so to talk about network densification, let me just mention there are two basic classes of networks that I want to outline here. And so the natural metrics are the number of nodes of a network and the number of links. And so the two classes are sparse networks. And so these classic preferential attachment networks fall into the field, into the arena of sparse networks. That is the ratio, the number of links to the number of nodes goes to a constant as the size of the network grows. But then there are dense networks, and these are networks in which the number of links to nodes, and this ratio is basically nothing more than a degree over 2. So the average degree is actually increasing as the network grows. These are two fundamentally different types of networks. And so let me show you now some data. And actually this, I don't know if any of you have ever looked at this paper, but it's by Leskovitz et al. It was a very well-known, this paper. But it's one of these papers that was written more than 10 years ago, and it seems as if it's not as well recognized as it ought to be. But here is a wide variety of systems, like for example, the archive network, which is just co-authorship networks in the archive. And what they're looking at, so the x-axis is always the number of nodes, the y-axis is the number of edges, and so you see that in all these different, the movie database, the email network of a particular university, affiliation networks, patent networks, that the number of edges or the number of links is growing as the number of nodes is growing, and so the mean degree of all these networks is growing. So this is the basic phenomenology, that there's a wide class of networks that are densifying as a function of time.
I just wanted to say that in math, for example, by dense networks, they mean when the average degree grows linearly, exactly linear. So it's a number of edges and square.
I see.
That's the terminology.
Okay, I would call such networks complete because...
No, they got longer.
Well, their distance is very small. But nevertheless, so these are all, by the way, so since you raise the point that these, in the case of the mathematics definition, the number of links is growing linearly with the number of edges, these are all different exponents. I mean, you can't read the numbers here, but they're all very different. Okay, so what I want to try and do now is introduce to you like an absolutely trivial model that accounts for densification and then outline some of its basic properties. So this is work only a year ago. And, so I guess what I'd like to say is that in some sense, the whole field of network science that started in the late 90s, and there was all this work on generative models of complex networks, and then people are now moving into applications. But nevertheless, there's still many open questions just in the most basic, simple-minded models of network growth. So even though this might seem like a blast from the past, I hope there's still a freshness to it. So here is our model, what we call the copying model. So imagine you have some existing network. This is kind of small, but nevertheless, it's a network of 3 people. And you want to join this network. So think of it as like Facebook, and you're joining Facebook, and you find a Facebook friend. So you are the new node, and you join up to this person here. And then, as you all know, since I'm an old fogey, I've only learned this very recently because I just joined Facebook like, a couple of months ago. Yeah, it's pathetic. It's really pathetic. But the point is that when I join Facebook, then after a while, so, Facebook will tell me, boy, we see that you're friends with your son. Maybe you'd like to be friends with some of your son's friends. So it's like, here I'm joining my son, and here are some of his friends. And then Facebook says, wouldn't you like to be connected to some of the friends of your son? So the idea here is that in this copying model, we say that there are two friends of the person that I've joined, and with probability p, which is independent, I will join to the friends of my friend. So with probability p squared, I join to both of the guys. But since these are independent probabilities, then with the probability p times 1 minus p, I just join to one of them. Or I could join to the other with one of them. Or with probability 1 minus p squared, I don't join to anybody. So this is it. This is the entire model. I pick a node at random, I join it, and then I join to each of its friends independently with probability p. And now I just want to investigate the consequences of this model. And even though the model seems so trivial, and we can now, many of you probably have an idea like how I might solve it, some very interesting mathematics comes out of this. It's a very interesting phenomenology. So again, why do we care about densifying networks or about this copying model? Because first it densifies, and it seems to mimic some of what happens in the dynamics of various types of social media. Okay, so first let me show you just some pictures of what happens to this network. So here is a network of 1,000 nodes, and this is with copying probability equals 0, so all I'm doing is generating what's known as the random recursive tree. I pick a node at random, I join to it, another node comes in, I pick a node and join to it. That is the construction known as the random recursive tree, and so this is just some representation of it, and you see that it's obviously a very tree-like graph. It's pretty well connected, and as I increase this copying probability, then you start to see a little bit of like hub-like action that's happening over here. As I increase p a little bit further, it's starting to get more dense, and here at 0.6, something actually, a phase transition has occurred. And in fact, this is actually a densifying network. And as I increase p further, now it's you can't even see what's going on. And then, of course, when p is equal to 1, we're generating a complete graph. So that's roughly speaking what the network looks like. But now what I want to do is look at this a little bit more precisely and enumerate, first of all, the phase diagram and some of the geometric properties of this copying network. So our phase diagram is on the axis of p. So from 0, that just generates a random recursive tree, to here we generate the complete graph, and here are sort of representative graphs, smaller graphs for different values of p. So for p very small, it's a very tree-like graph. For p equals 1, it's a complete graph. And we want to try and characterize what happens as p goes between 0 and 1. Oh, question, yeah.
What is the initial network you start from?
Just a single node.
Ah.
Yeah, I mean, the starting node really doesn't play much role. I mean, the starting state. So first of all, let us study the number of links as how it depends on n. And it turns out, and I will derive this momentarily, but here I just want to give you an overview. It turns out that for p less than 1/2, the number of links grows linearly with n. So this is the sparse regime. But when p is larger than 1/2, the number of links grows at n to the power 2p. And so this qualifies as a densifying network because it means that the ratio of links to nodes grows as a positive power of n when p is larger than 1/2. But then once you start saying, well, if I looked at links, in some sense that's like the simplest complete graph. It's a complete graph of just 2 nodes and 1 link. But one can look at triangles. And it turns out that triangles also have another phase transition at p equals 2/3. So for p less than 2/3, triangles and links scale in the same way, but beyond that point, triangles scale faster than the number of links. And then once you see this game being played, you can look at like complete graphs of size 4, which has a phase transition at 3/4. Below this point, number of complete graphs of size 4 grows linearly with triangles. Beyond this point, it grows non-linearly. And there's an infinite sequence of phase transitions where complete graphs of size m have phase transitions at point m minus 1 over m. And so one has this kind of sort of infinite series of phase transitions that exist in the model. So this is an overview of the geometric structure. And now let's try and look at this in a little bit more detail. And by the way, again, so this green regime is what I call the sparse regime. Here's the dense regime. And inside the dense regime, there's all these phase transitions. It's all very, it's mathematically fascinating. So this is probably like maybe the most important story in this slide in the talk in some sense. If you understand the slide, then everything else follows naturally. And so let's look at the behavior of the number of links in a network of n nodes. And so, as he said, I like to write down master equations. I like to write down evolution equations. So let's ask how the number of links, when I have n plus 1 nodes, how does it change when I add one more node to the system? So I have the number of links when there's n nodes, the number of links when I add one new node in the network. How does it change? There are two ways it changes, because I first attach to somebody randomly. I'll attach to you. And so there's obviously a +1 on the right-hand side. But then I attach to some of your friends. And since you're a very gregarious guy, you're friends with everybody here. And so I'm going to have to attach to like some finite fraction of everybody in this room. So there'll be a term 1 plus something that's proportional to your degree. So let's look at this. So here's Dima, who's got lots of friends. And so I have 1 because I attached to Dima. But then I attach to, with probability p is k friends, and I attach to each one of them with probability p. So the right-hand side of this equation is clearly 1 plus pk. So that's it. And then what I should do to find the average, because here was the average number of links, I should compute the average degree of the person I have to attach to. And the average degree is just the number of links divided by n. So a very simple difference equation, but because there's of its structure, it has a very rich solution. And so here is the solution to this recursion formula as a function of p. For p less than a half, L is linear n. And for p a half or larger, it's growing non-linearly with n. So this is the basic phenomenon that the network densifies as a function of p, as a function of n when p is larger than 1 half. So, you know, if you buy this, then a lot of what I'm going to show after this is commentary, because it'll just be the same mathematics, maybe in a slightly more complicated setting. Okay, so again, for p less than a half, the network is sparse. For p larger than half, the network is dense. So we can now look a little bit more detail. We can look at the variance in the number of links. What does this guy do? And so here's the equation for the variance. It's a little bit more complicated. And let me sort of walk you through some of it, because what we need to do is you have to compute, so this L with a subscript and not L with an argument is just in a particular realization of the network. So if I have a network of n plus 1 nodes, the number of links is the number of links when I had n nodes plus 1 when I attach to Dima, plus A is meant to be the, in a particular realization, how many of his friends I attach to by this copying mechanism. And then I have to square it, so that's that. Then I have to average it, which is this. And the average involves the average over the degree of u. And so there's a little bit of like binomial gymnastics here. It's straightforward and a little bit tedious, but you know, I hope I give you get a sense that doing all of this, you can then get to this point here. And the one problem with this equation, though, is that it's not closed because it involves a second moment of the degree distribution, which I don't know. And so even though this equation is like in principle formal, we don't know how to solve it in all detail. But nevertheless, what we can say is that when the network is sparse, this is a finite number and it doesn't affect the asymptotics. And so for p less than 1, it turns out for less than 1/4, one gets linear growth of the variance. But there's this anomalous behavior, and one has to do a little bit of fiddling around to like how do we deal with this red term over here. But it's a mathematical detail that I don't want to go into. But the main point is that this variance is kind of like normal. In this regime, we expect there might be a Gaussian distribution in the number of links. But beyond 1/4, we have this anomalous scaling, and so it looks like a non-Gaussian behavior. And here is just kind of what you might expect, but it's also quite striking, which is if you look at the distribution of the number of links as a function of p. So here I'm plotting the distribution of the number of links as a function of the scaled number of links in the system, so I divide by the average. And so when p is small, it's a very tight distribution, and it's actually a Gaussian distribution about 1, because I've properly scaled it. And then you see that at point 3 it widens At 0.5 it widens further, at 0.7 it's even more wide, and then 0.9 is starting to get narrower again. So this variance in this length distribution is very sharp, widens in some point that we don't know where is the maximum, and then it gets narrow again when it go to the complete graph limit. So it's a very weird phenomenology that comes out from, again, an unbelievably trivial growth mechanism. Let me just mention very briefly what happens if you look at the number of triangles. This involves a little bit more combinatorics, but let me at least outline what happens so you get a flavor for what's going on here. So again, here is my initial network, and here I'm going to join to Dima again, who's over here. But now in this particular instance, instead of like Dima sort of being like the godfather of all of you, and you guys don't talk to each other, some of you guys might talk to each other at some point. So there's some links here among the people here sitting in the audience. And we call these things clustering links, and you'll see why in just a moment. So let's suppose this is our starting network, and we want to ask, how does the number of triangles change when I attach to Dima, and I also make some copying links to some of you out in the audience. So let's suppose that I copy to these three people. So first point is that you see that wherever I make a copying link over here, because Dima was connected to say you, and I'm now connected to you, we now are part of a triangle. So that's one mechanism for making a triangle. Oops, something went on the floor here. Oh well. So there's one triangle created that way. And so there's another triangle created if I pick like someone else in the audience. So those are the ways that whenever, for each one of these copying links, there's a new triangle created. But the point is that there's also a possibility of creating a new triangle by this way. So here's the shaded triangle over here. That's another triangle that's being created. And so there, in this particular case, we created 4 new triangles, one each for each one of the copying links, and then an additional one because of the presence of this extra link between maybe 2 people in the audience. And so here is the change in the number of triangles. So again, A for a particular realization is a number of these dotted links. And then there is, because of the presence of these clustering links, this is a number of additional triangles that are created. And I don't want to go into the details of this. I'm happy to answer it or derive it after the fact, but it's just a simple combinatoric thing. So it's the increase in the number of triangles with each new node addition with the direct link and the copying links. And so then one does like the usual thing of trying to now average this over the degree distribution. Again, it's some very straightforward but a little bit tedious binomial gymnastics. And at the end of the day, one can then compute the increase in the number of triangles. This guy over here. And so from this, we can now write down a master equation or an evolution equation for how the number of triangles when there are n plus 1 nodes in the network, how this relates to the number of triangles when there are n nodes in the network. And once we have this equation, then we can start like trying to solve it. And so here is the solution to that equation. And so this shows very rich behavior with multiple phase transitions. At p equals 1/2, there's a logarithmic correction. It grows as n for p less than 1/2, as n to the 2p for p between 1/2 and 2/3. But notice that these two behaviors are the same as the number of links. So here in this whole region, the number of triangles grows linearly in the number of links, and then it grows non-linearly beyond 2/3. And there's an additional logarithmic correction here. So it's very rich phenomenology with kind of very little, like, modeling work. It's just a little bit of, just bashing your head against the wall. But it works. So now let me mention to you the degree distribution, which, for a place like this is the, the citadel of the degree distribution. So, one can ask, well, what is the degree distribution of this model? And it turns out that it's also very weird. So here is, so nk is the number of nodes of degree k, and I'm asking how the number of nodes of degree k changes every time I add one new node in the network. And this is the way I always write these master equations, because there's no time variable here. The only variable is the number of nodes in the network, so we use that as a time-like variable. So if I attach to a node of degree k minus 1, then I will create a node of degree k by that attachment. And the probability of attachment is such that a node of degree k is just the number of nodes of degree k minus 1 divided by n. So this is the gain in number of nodes of degree k. This is the loss term, because if I attach to you and you have already degree k, I've now made you degree k plus 1, and so we lose nodes of degree k. So this is just the initial attachment. There's a similar induced preferential attachment by the copying mechanism. And then there's this very weird non-local term, because I can ask, if I'm now the new node and I attach, well, I attach to Dima, I have no idea what my degree is going to be, because first I have to ask, what is your degree? And then I attach to a fraction p of all of his friends. And so this is just the degree of the new node, and it can be anything between k minus, if I'm looking at the number of nodes of degree k, then I can, if you have degree k minus 1, then if I attach to you and all of your k minus 1 friends, then I create a node of degree k. But if you have a node of degree of 10 million k, then I still attach to you and only attach to a tiny fraction of your friends and create a node of degree k. So this is a non-local term involving all possible combinations of what is your degree and the probability of attaching to create a node of degree k. So this is the equation, and so it's non-local, so that's already a problem. So here's like a little graph to try and illustrate it, because if I want to create a node, if I want to have my degree to be 5, then here you had 1, 2, 3, 4, 5, 6, 7. You had degree 7, so I'm doing something with a node of degree 7 to create a node of degree 5. So it's a non-local term case. So here's the most trivial way that you can deal with it, which is like, and so I can just, I keep forgetting about this thing that doesn't work. So just replace it by a single term. So for example, if p is 1/2, and if you have a million friends, and I want to create a node of degree 500,000, I attach to you, and I attach to half of your friends. And that's precisely what this term is, which is saying that even though this is a non-local term, there's a most likely event that if p is 1/2, for example, and you have a million friends, I will create a node of degree 500,000 by attaching to you. And so that's all that's happening here, is that I replace this infinite series by one term, which is nk over p. So if k is a million, you have a million friends, and p, I'm sorry, I said it backwards. But anyways, I'm just creating, a node of degree 500,000 by attaching to you, which you have a node, you have degree 1 million. And so if you make this assumption, then, and assume that the distribution is a power law, you'll find it's a consistent solution, and in fact you'll find a power law degree distribution which has a transcendental equation for the exponents. That's also kind of weird mathematically. But the other thing about this is that it shows normal scaling. That is, if I plot the density, so little nk is the density of nodes of degree k, capital NK divided by capital N. That as n gets larger, this goes to a normal scaling limit. It happens incredibly slowly though, and I don't know why it happens so slowly. But there's a power law degree distribution ultimately that emerges. However, for p larger than 1/2, and I forgot to say here that in the sparse regime, this assumption is self-consistent and you end up with this power law degree distribution. But in the dense regime, we know nothing. And all I can show you is just data that shows that here's an attempt to try and make a scaling plot. It shows that it doesn't scale, it's very broad distribution. We have no idea how to describe this mathematically. So if anybody wants a good project, here it is. Tell me the degree distribution of this network for p larger than 1/2.
Do you have a plot of gamma as a function of p? Is that a solution?
Well, I mean, it's like,
it should go to infinity.
so it starts at infinity for gamma equals 0, and then it goes to -2 when gamma equals 1. I'm sorry, as a function of p, when p is equal to 0, gamma is infinity. So it's like it's an exponential distribution because it's a random recursive tree. And when p approaches 1/2, this number goes to 2. So yes, we do have data for like 1/10, 2/10, 3/10, 4/10 that kind of fits this, but we didn't like try and do like a very careful fit to this because it was. That was sort of the least interesting part of this model. Okay. The last thing I want to mention about this very simple model is what happens when you include second neighbor copying. So the original model is I attach to Dima, and then since he knows all of you, I then attach to some of you randomly. But you could say, well, once I do this copying process, well, why not just sort of iterate it? Let's look at the friends of your friends. And so I attached each of you with some probability, and then you have friends all around the world, and maybe I want to attach to some of them as well. What happens if I allow second neighbor copying? So let's imagine we connect to neighbors with a target of probability P, connect to the second neighbors with probability Q, where Q is some other parameter. And again, this model comes out from just being my very minimalist interaction with Facebook, which every once in a while they send you some message. Well, we see you're friends with so and so. Wouldn't you like to be friends with so and so's friend? And so just iterate this, and that's where we get to. So the main point about this is that for any value of Q, the network becomes complete. But what I mean by complete is not exact, it's not perfect completion in the sense of mathematicians complete, but what it means that the number of links scales quadratically with the number of nodes. So let's try to show this. So the way it turns out, it's actually a very simple probabilistic calculation. So let me call C sub n probability that the network that if you start with a network, a complete graph, perfect complete graph. So I mean now mathematically complete, that there's n combination 2 links for a network of n nodes. So the probability that an n complete graph remains complete when I add one more new node to the network. So in the original copying model, if we were all a complete graph, and I mean I'm not part of it yet, but I joined DEMA and then I attached everybody, that would be complete. But if I allow now second neighbor copying, we want to ask, now it's less stringent to make the network complete, but let's see how that can happen. So there are sort of two terms in which to make the network, there's two ways to make the network complete. So first way is that by nearest neighbor copying, so I attach to DEMA, and now, let's assume that everybody knows, well, actually everybody does know everybody in this room, right? Except for me. I'm the only person you don't know yet. Anyways, so everybody knows everybody else. So I attach to DEMA, and then I attach to K of you. So the network is not quite complete. So this first term here is the probability that I attach to K of you. And now in order that the network is complete, once I attach, say, to you, then I'll have to attach to your friends by the second neighbor copy. So the second term is to ensure that for the n minus k, so I copied a k of you by this first neighbor copying by going to DEMA. I have n minus k guys who are now, that I don't know yet, and then this term, it counts for by the second neighbor linking that I attach to all of the remaining n minus k people. So it's a very simple probabilistic formula here, and now we can do some asymptotic analysis of it. And the crucial point is that this is a binomial factor, and when n is large, it's a sharply peaked about the most probable value. And so if you make that kind of approximation and then do some very simple asymptotic analysis, all of this stuff boils down to something which looks like a double exponential form. And then one can ask, what we want is that the product of all of these C sub n's, because C sub n is the probability that we start with n people, I'm the new person, I come into the room, and at the end of this seminar, I'm part of a complete graph. And then the next seminar speaker comes on Monday, and then you want them to be part of the complete graph. You want to have this happen over and over again until n goes to infinity, when you've had an infinite number of speakers here. So what I want is this completeness probability, which is this product of this times Roman C, product all the way up to n. This is meant to be calligraphic C. So this is the probability that a network that up to n nodes is complete. So we have to compute the product of these C sub n's. And normally what you do when you have products of these things is you write the product and you write this thing as e to the logarithm, and then the sum becomes the product becomes a sum, and then you take the continuous limit. So e to the integral of what was the logarithm over here. And then the basic question is does this integral converge or diverge? And it turns out that in this particular case, this integral is convergent, which means that this product is non-zero. So there is a non-zero probability that when I have second neighbor connection, the network becomes complete. So it's kind of a very strong statement that if you have this copying process that can go beyond nearest neighbors, eventually everybody will know everybody. But what I mean by everybody knowing everybody, so this is now numerical data just to give you a sense what I mean by this, which is that it means that everybody knowing everybody means that asymptotically the number of links scales at n squared over 2. And so here is some data that shows that, for example, for p is, and excuse me, there is a, there's a notational glitch here, because what I mean by p is 0.3 is q is 0.3. And so this is the second neighbor connection. And so you see that it starts off that the number of links grows roughly linearly with n, but then there's some crossover phenomena. And then if you wait long enough, eventually it scales like n squared over 2. So what it doesn't say, though, is that it's, you know, like a true complete graph would be n squared over 2 with the coefficient 1. And I don't have anything to say about the coefficient, but it's just the scaling is going like n squared over 2. The coefficient can be arbitrarily small if q is small, but nevertheless, crucial point is this completeness transition. And you see that for p even smaller, you have to wait a really long time. I mean, this is sort of, you know, beyond the scale that we could do any simulation to see the asymptotic behavior. So this is the whole story about densification, and this is sort of maybe the first 60% of my talk. So
it
yeah.
depends on n, where it does the crossover, or does it have?
Yeah, I mean, the point is that this, so this I have to say I don't have an answer for, but you see that as p gets smaller, the large value of n at which crossover occurs is increasing, but how the scaling goes p versus n, I don't know.
This is q.
Yeah, I'm sorry, this is q, this is the second
What is
neighbor.
p?
Pardon me?
What is p?
What is p here?
Something. It's fixed.
Yes, that's right. Yeah, I mean, I have to say that, yeah, don't know. But I think it might be 1/2.
Didn't you want it to be somewhere in the sparse version when you start? The p?
It should be less than that.
Well, no, the point is that no matter what, you know, again, the statement is that no matter what p and q are, as long as q is non-zero, eventually it will cross over to this completeness transition. So you can even be in the sparse regime, but because of the second neighbor connection, it eventually takes over. Okay, so let me now turn to the second half of my presentation, which is the mysteries part, and I want to talk a little bit about the mysteries of this redirection process. And you know, this is a weird place to be describing preferential attachment, because you know, this is the citadel of preferential attachment. And let me just, but the crucial point here is that what we found already like 15 years ago was that there is a way of generating preferential attachment networks in an incredibly efficient manner. And if you haven't seen this before, then you know, I argue that you're going to speed up your simulations by many orders of magnitude, because one can generate linear preferential attachment networks by doing uniform attachment. So I uniformly attach to you. But then I say, well, I'm not sure I like to be with you anymore. Who's one of your friends? And then I just attach to one of your friends. That simple mechanism generates linear preferential attachment. And if you don't know this, I mean, it's an important lesson to appreciate. And in fact, there's sort of a very good sort of case study about this, which is suppose that there's a deadly virus. And, you know, I don't know, there's like 20 people in this room, 25 people in this room, and I have like 5 antidotes. Who should I give the antidote to maximize the chance we're all going to live? And what I should do is that I pick you at random, and I say, who is one of your friends? And I don't know who's one of your friends? Okay, I give him one of the antidotes. And the reason why that works is that, you know, typically the number of friends that Maxime has is going to be on average higher than yours. It's called the friendship paradox. And so it's better to like vaccinate somebody who's got lots of friends because they interact with a lot of people. So this is the mechanism whereby by looking at somebody randomly and then redirecting, you actually generate preferential attachment. In fact, you generate something called shifted linear preferential attachment. So as, you know, it's worth, you know, giving homage to history, preferential attachment was first discovered in a very strange way by Yule in 1926, looking at paleontological data. Then Simon in 1955 essentially solved the problem, but he didn't know it, you know, it was in a very weird context. And then the famous Barbarossa Alba paper in 1999 So all of this is preferential attachment, but I want to now talk about some additional mysteries of this redirection process. But before I get to that, let me now just make it a little bit more mathematical and clear what I have in mind about this purple discussion, this uniform attachment plus redirection. So let's imagine we have an arbitrary directed network, and here is the redirection mechanism. A new node wants to join the network, and so he picks a random target. So I pick you. And with a probability 1 minus r, I will join C. But with a probability r, I join to Maxime, because you are friend to Maxime. And so I join with probability r to an ancestor network. So the crucial point is that the ancestor node, how many ways can I join to the ancestor node? I have to look at all of its upstream neighbors. It's got this guy, and that guy. So the rate at which this guy will actually get attached to by this redirection mechanism is proportional to the number of its upstream neighbors. And this is what induces an effective linear preferential attachment. So let me now write down the master equation that describes this cartoon. So the probability 1 minus r, I attach randomly. So probability 1 minus r, I attach to node degree k minus 1 with the probability nk minus 1 over n, and I create a node of degree k. With probability nk over n, I attach a node of degree k, and I lose a node of degree k. That's why this is in red for loss and black for gain. And then there's also the delta k1, because I'm always creating one node of degree 1 by this process. But then because of the redirection, there is the second term, which is this induced preferential attachment, which is proportional to the number of upstream neighbors of a node. So a node of degree k minus 1 has k minus 2 upstream neighbors, and that's the rate at which I attach to it. And then you just rearrange this. There's nothing, this is just trivial algebra. And you see that the term in front of nk is like linear nk plus some extra little stuff here. And so this is what I call shifted linear preferential attachment, in which the attachment rate is proportional to k, equal to k, plus this additional shift, k plus lambda. So again, if you want to generate preferential attachment graphs, it's basically two computer instructions. Pick a node at random, attach to the friend with a probability 1 minus probability r. And then you generate shifted linear preferential attachment. And if you choose r equals 1/2, you generate perfect linear preferential attachment. So, from a computer science perspective, this is kind of a very surprising consequence that you can start with what seems to be a hard problem. How do you pick a node according to linear preferential attachment? And you do it by just one step. Anyways, so let's now talk about the degree distribution. So here I'm writing the master equation for general attachment rate, a sub k. I've written it in the general form. So the rate at which nodes of degree k are born is proportional to the attachment rate to node of degree k minus 1 times the number divided by the total attachment rate. And so this is the master equation. And the trick here to solve this problem in a very appealing way is to notice that that there's a natural scaling, that the number of nodes of degree k is proportional to n, again for a sparse network, times a density, little n sub k. If you make this assumption in this, you can then transform this to just a linear set of recursion formulas, and you can just solve with high school algebra. And so this is the formal solution to the degree distribution. Now, in this form, it's a form of an infinite product, and the crucial point is that there's a right way and a wrong way to deal with this infinite product. And the right way is to notice that for this type of attachment rate, this can be written in terms of ratios of gamma functions. And once you do that, everything is very simple and all the asymptotics is really clear. And if you don't do that, you can end up with lots of gymnastics that you don't need to do. Anyways, so, and if anybody wants to know a little bit more about how this turns into a gamma function, I'm happy to show it because it's just so beautiful and so helpful. But anyways, once you have in terms of ratios gamma functions, you can then extract the asymptotics easily, and you get this non-universal power law. And so let me now just stop for a little commercial break here because, again, I grew up in the world of statistical physics. And when I was a graduate student, it was renormalization group, universality, short-range details don't matter. You integrate out local degrees of freedom, and there's long-range correlations, and they're universal, independent. But notice here that this exponent depends on this additive shift. So you might say, well, who cares if the attachment rate to a node of degree 1,000,000 is 1,000,000 or 1,000,000 plus 1? Why should I care about that one? And it turns out that in this particular instance, it actually matters in a very profound way. So, in all this complex network business, if the attachment rate is sublinear in K, that is the universal regime where one gets a stretched exponential degree distribution. If it's superlinear in K, you end up with basically a condensation transition. When it's linear in K, which is like, you might think, well, then the short-range details don't matter. Then the short-range details actually matter incredibly powerfully. Because notice that if there's a lambda equals 1 here, who cares if the attachment rate to a node of degree 1,000,000 is 1,000,000 or 1,000,000 plus 1, but it changes the exponent by 1. And in fact, it's even worse than that, which is that suppose I just change one attachment rate. So I have attachment rate k for all k bigger than 1 at just some number alpha. And again, you can go through the kind of mathematics that we know how to play with of solving for the degree distribution. So you end up with something. The upshot of all of this is that the exponent of the degree distribution is non-universal. It depends on this number alpha. So change one attachment rate, one out of an infinite number of attachment rates, it actually changes the degree distribution in a profound way. And in fact, I don't have a slide for this, but because it even fills up more space, but you could say, well, maybe it was important because this was one of the starting attachment rates. Suppose I take the attachment rate of a node degree 1,000,000 and make it, instead of 1,000,000, make it 1,000,000.1, and everybody else is linear. You still get some formula like this. So it's incredibly delicate. And why it's delicate ultimately arises because there's an underlying multiplicative process that governs the growth of these networks. When you're dealing with multiplicative processes, they're very non-universal. Okay, so anyways, that was all kind of like advertisement because now I want to come to the last part of my talk, which is just what happens when you have an isentropic network. Because this redirection mechanism worked really beautifully for directed networks, but if we're talking about friendship networks, then hopefully if I'm a friend of Dima's, he might consider me to be a friend. I hope that's the case. So in some sense, we don't have arrows on these links. We have just this. And so I want to ask, what is the role of redirection for an isentropic network? Because this is maybe more relevant to a social network, which is that, if I want to attach to Dima, then, since it's a two-way street between us, then, after I maybe provisionally think, well, should I be friends with you? Oh, I think I better be friends with Maxime. So that's basically what I'm trying to do here, which is that you pick a node at random, and with probability 1 minus r, you attach to it. With probability r, you attach to its friend. So one feature about this model is that it has one parameter, r. And when I do like modeling, I usually like to have no more than one parameter. For me, 1 is already a big number. But in fact, let's now even go to a 0 parameter model, which is let's choose r equals 1. Let's have perfect redirection. So I'm going to pick somebody in this audience, you again. I'm sorry picking on you. And
You always do that.
yes, I know. And then I become friends with Maxime, and I just forget about Dima. So that is the model. And let's ask, what happens in this model? So the first point about this model is that it's very trivial to state. I pick a person at random, I attach to one of his friends. There's no heterogeneity in the model. There's just like a very simple homogeneous model that's stated in 10 words or less. So what is the outcome of this model of certain redirection? And here's the outcome. So here's just like 3 random realizations of the network. First point is that it's not at all homogeneous. It's incredibly hierarchical in its structure. So you see that there's a hub here that has degree bigger than, so I forget, these are nodes, these are networks of 5,000 nodes. So there's 2 hubs, well actually 3 hubs that have a degree over 1,000. There's lots of leaves, these are nodes of degree 1, and there's lots of other fluff here. This looks nothing like any network that one sort of sees in an archetypical complex network talk, I think. But the crucial point here is that the network is highly heterogeneous from a homogeneous group. Another feature about this network, which is really bizarre, is that it's not even like thermodynamic in some sense. So what I'm showing here is the degree distributions of nodes of fixed degree. So here is nodes of degree 2, 4, 8, 16, 32, and so on down the road. And I'm plotting on a double logarithmic scale. And then what the C is here is this is the sum of the number of nodes of degree 2, 4, 8, dot, 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 all the way up to the end of the network, and divided by 10 to the 4th, so it falls in the same curve. And you see that all the data is very linear, there's not any fluctuation in data. And if you look at the slope of this, it turns out to be 0.565. So it says that by this mechanism, most of the nodes in the network are, we talked about sparse networks with the number of nodes of any degree grew linearly with n. We talked about densifying networks with the number of nodes, well, let's leave densifying out of it. But just in normal sparse networks, the number of nodes of any given degree is growing linearly with n. Here they're growing sublinearly. So that's mystery number one. Why is it that this network is not growing linearly with the size, the number of nodes of any degree is growing sublinearly with the size of the network? So the main point about this very simple rule is that you end up with a nucleus. What we call the nucleus is nodes of degree 2 and higher. This nucleus is sublinear in the network, and almost all nodes in the network are leaves, nodes of degree 1. So there's this huge number of leaves and a little bit of other stuff that's sublinear. So let me now just try and give you a flavor like how we might try and attack this problem, because here the problem is unsolved. I'm leaving this as an open question, since I'm coming to the world's citadel of network science. And so this is a problem that I've actually been thinking about for more than 10 years, and I've failed so far to make any progress. But let me give you a sense of some things you might try and think about. So let's look at the certain redirection probability model, and let's ask, what is the probability that you make a perfect star? So how do I make a perfect star? So here is, say, the first node of the network. Node number 2, well, it can only attach this node, the central star, so it's attached, so here's node number 2. Now for node number 3, it doesn't matter if I attach to this guy or that guy, I always redirect, and the outcome will always be a little 3-node star graph. But now to make the next term in the star, well, how do I do that? I would attach to this guy or that guy, and then because I always redirect, I'll redirect to the hub. So there are 2 leads and 1 hub. So with probability 2/3, I'm certainly going to redirect it to the hub. So so here it is. With probability 2/3, I will build a star of n equals 4 nodes. But then once I make this, then there's 3 leaves, so 3/4 of the time I'll attach to a leaf, and then I'll redirect to the hub. So I do this with probably 3/4, and then 4/5, and you see the pattern. And so to make a star of n nodes, it goes down like 1 over n minus 1. So it's pretty easy to make a star. So this is already like a clue that there's something weird about this redirection model, because you would normally think that such a unique object should occur with an exponentially small probability. It's only a power law small probability. So now let's ask about, well, in real life we don't make perfect stars. You might make a mistake. So what happens when we make a star with a defect? So here we are, we're building our star up to like a point K, and then at the Kth point we make a mistake. And to make a mistake, what happens is that instead of attaching to one of the leaves and then redirecting to the hub, by mistake I attach to the hub and then I redirect to one of the leaves. So here's my mistake. And then I continue making the rest of the perfect star. And so we can ask, what is the probability of making this defective star? So we know the probability of making a perfect star of k nodes is 2 over k minus 1. Then I make this mistake, which when I have now a total of k plus 1 nodes, then I attach to the center with probability 1 over k plus 1. So this is the mistake. And then this is the probability of then creating the rest of the star perfectly all the way down the road. So again, it kind of looks like this product, but you see this 1/2 here, and it's a very simple probabilistic calculation. And again, if you're used to dealing with gamma functions, then you look at this and you know what to do with it. It's a ratio of gamma functions. You can then extract the asymptotics from it, and then we want to say, well, this is just the problem of making a perfect a slightly, almost perfect star, but with an error at the k point. We've got to integrate over all places that we're going to make the error, so we have to integrate over all k. And at the end of the day, one ends up with 1 over n. So this is the main point here, is that it's very easy to make star-like networks. They're all over the place. And so this is, at least I think, the very first step in trying to understand like why it is that these networks are so anomalous. First point is that stars are very easy to create. And you see here 4/3 n, 1 over n, compared to a perfect star, which was 2 over n. So a slightly imperfect star is almost as likely as a perfect star, and you can do this for like 2 mistakes, 3 mistakes. They're all scaling like 1 over n. Okay, easy to make star networks. So I'm basically at my end now, and so let me just sort of give you a very simple summary. I hope I've given you a sense that densifying networks by this copying mechanism is phenomenologically very rich. We understand a lot about things like small motifs. We don't understand anything about the degree distribution. And there's all kinds of unexplored applications. And in fact, the original paper by Leskovitz and company, I mean, we're now trying to look at some of the data sets there to see if some of the phase transitions that we see in our copying model actually can occur in the data. And the brain is another example of what might be a dense network. We have 10 to the 11th neurons in the brain, I think, and we have like 10 to the, how many connections? What? Yeah, I mean, the point is that the mean degree in the brain is roughly 10 cubed when you have 10 to the 11th neurons. So is that in the dense regime? Is that it seems like the degree is scaling like n to the 1/3 or something like that. I don't know if that's true or not, because one should look at overall taxa. But it seems as if there's a possibility that the brain could be a dense network. This growth by redirection, I hope I've given you a little bit of a commercial message that redirection for directed networks is a very simple and very powerful algorithm. And it's a funny thing because maybe some of you know Hovland's book on networks. And in the appendix, there is a very careful and nice discussion of how to generate preferential attachment networks by, an algorithm that goes like n log n, in which you have to search all the nodes in the network and pick a node with probably linear proportional to its degree. And so they're very proud of it, except that it's a factor 10 to the 4th slower than our algorithm of just doing it by this redirection mechanism. Another important message is the non-universal behavior of linear preferential attachment. This is a message that I tell people whenever I give talks about this, and especially here, I know this is maybe almost a heretical statement to make, but it's worth emphasizing. And in the case of certain redirection, this is kind of an open problem. We don't know what is the exponent, we don't understand the scaling here. It's a system that does not show self-averaging. Each realization of the network is its own universe. It's like imagining you have exoplanets and you start life on Earth, and we have 10 digits, but you start life on some planet over there and they have 23 digits, who knows? But the point is that there's no self-averaging, so it's very hard to try and make thermodynamic statements about this class of networks. Anyway, so I hope you've enjoyed, and thanks for your attention.
Thank you, Sid, for this heretical talk.
My pleasure. I'm an old fart now, I can do whatever I want.
Okay. So let us see if they have any questions. Yes.
Okay.
And when you were talking about the redirection, you were talking about upstream nodes?
Yes.
But in the formula that you showed for dn k over dn,
Yeah.
you just had nk and nk minus 1.
Right.
And it looked like it would work even if you did not have directionality.
No, I mean, so the thing is that you could attempt to do the same thing with non-directionality, but it turns out that the equation involves, it's not closed. It's just, I mean, I can show you, but it's just, you try and do it and it involves because it involves the inverse moment of the degree distribution, and we don't know what to do with it. So, yeah, I mean, you can formally write down an equation, but you can't do anything with it. Or at least, let me put it this way, I can't do anything with it.
And the direction here is really just the older nodes, right?
Correct, yes.
Right.
Do you have a sense of how this redirection network growth process would affect, say, an existing network? So an intervention on an already existing network or some sort of link rewiring or massive capacity?
So you're saying that once you have an already existing network,
Yeah.
and then you continue growing it by this
Or
redirection?
isn't it growing it, but a sort of a redirection processing only links locally?
So I'm not sure, I'm still not sure I understand the question.
I'll think about it and rephrase it.
Okay, but you can, if you think about it in the next 30 seconds, you should do it again. Yep.
I have a bit of a question. So you have these nice thoughts about what happens in the copy model if P is below 1.5 and above. or
Right. 1/2.
1/2.
Right.
Do you have a pithy answer to what the behavior is like kind of right below versus right above?
Well, I mean,
Like not all the way up to 0.6 maybe, but like, okay, like here we have what's the difference between 0.49 and 0.51?
well, I guess the problem, the point is that if I want to compare between 0.49 and 0.51, first of all, you'd have to go to a very large network to really see the difference, because the point is that the number of nodes, the number of links is growing like n to the 2p. So if p is like 0.51, so the number of links is growing like n to the 1.02, you're going to have to go to like n like 10 to the 20th to see that that's different than like n to the 1 with a large coefficient. So it's very hard if you wanted to say like if I'm at 0.49 and 0.51, how do I see the difference? I would say you have to there'll be some crossover value of n where then the difference is apparent, but that crossover value of n will like diverge as p approaches 1/2. And what that value of n is, I don't know off the top of my head, but I'm sure we could put our heads together and figure it out.
I really enjoyed the copy model and how you could get the local clustering to occur there. And I'm wondering if you have any intuition what would happen if instead of, in the beginning when you meet one friend, you attach to them, you can meet multiple friends, so you can kind of globally search the network, and then the copy would occur on the people that you attached.
No, I'm not, so again, let me make sure I understand your question, which is that instead of picking on Dima, I pick on Dima and you simultaneously, and then I connect to all of your friends with probability P.
Yeah.
Geez, that's a very good question. I don't know. I mean, I have the suspicion that might actually has a chance of being complete, but that's a really good question. So no, I don't know. I'd like to follow that up.
Any other questions? I got one more. Did you try to look at the limits, like because in particular in dense regime, the graph should converge to some limit, some graphon in which all edges are independent. Do you have any feeling?
Well, the first point is that I guess I would disagree that it should converge to something, because in fact we typically find non-self-averaging. So each realization network is like its own universe, and there's no notion of it. I mean, the one thing that I did spend some time on was not successful is looking at limit p going to 1, because when p equals 1, it's a complete graph. So for p close to 1, it's some perturbation on the complete graph that should be analytically tractable. I failed.
If no more questions, let's think.